Welcome to this Chapter 15 video where we discuss memory address translation, and let's begin. So, what we have here is we've got a problem where we need to have memory address spaces for multiple processes. Each program will use these addresses to access memory, but the addresses whenever they're actually used are used by instructions that are created, and the addresses are defined at compile time. Now, if we have programs that are being built for specific addresses, we can't have two programs that are loaded in the same address, especially if they're the same process. So if we can't load two programs at the same time, because the second program will actually be overwriting the first, we need to figure something out. Now, we could use static address relocation. Static address relocation is where a program called the loader, part of the operating system, will actually load the program from disk, and as it is loading it, it will rewrite the addresses in the program. Now, this can only happen during the loading stage. You can't really do this very well after the program started running, especially if the program is using things like pointers in the heap or in the stack. Those things are almost impossible to change after the program is loaded, because what's to define whether or not a particular value in memory is an address or something else? But this still doesn't prevent a rogue process from accessing memory of other processes. Just because you rewrote the addresses doesn't mean that a program can't try to go rewrite an address somewhere else. So let's see if we can find a better way to do this. Now, to do whatever we come up with has to follow three rules. The memory system has to be efficient. So whatever we're using, the instructions have to be able to access their memory data very quickly. There can't be any delay. It can't go through a lot of process. It actually should be faster than the operating system is, which means no software can be run. So we're going to find a solution that has low latency. We should find a solution that allows us to control what the process actually has in the way of memory, or has access to in the way of memory. A process should not be allowed to access memory that is not assigned to it. Absolutely should not. This includes other processes as well as the operating system. The operating system should be safe from rogue processes, so we need to implement something that allows control. And then finally, we need something that's flexible. Now, this flexibility means that it seems very odd that we have control and flexibility here. Flexibility is allowing the process to be able to use that address space in whatever way it wants to. It should be able to read or write to the addresses that it's allowed to without any extra work. And we call this transparency. As long as this memory access is transparent to the process, we've met this goal. Transparent meaning that the process thinks it's the only process running in memory at that time. We're going to start with something called the base and bound register. These are two registers that are set in the CPU that identify the address space of a particular process. These are hardware registers, like I said, in the CPU that are used to convert what we call a virtual address into a physical address. So we're going to take a virtual address, take this little bit of code here, which starts at address 100, and then performs a load operation at 104. What it's doing is it is adding the program counter and 300 and storing it into the stack pointer. And then the stack pointer is accessing a relative offset of -4, and it's trying to load this memory. So if this is starting at 100, the program counter, when it's running this instruction, is 104, always the next instruction. So 104 plus 300 gives us 404. Now we're loading a relative address of 404 minus 4, so 400. So here's our virtual address. We're trying to load data from this address. The registers are set in this manner. There is a bound register. This bound register identifies the size of the particular address space of the process. In this particular case, we have a 16K value here. This means that we have this process has 16 kilobytes of memory it can access, and every address must be within 16K. So first thing we're going to do is check this bound register. Is it less than, is the bound register greater than the virtual address? And as we can see here, 400 is definitely less than 4,000. So this is successful. We continue with the address translation. The second register is the base register. This is the actual physical memory address where the process's memory or address space starts. So in physical memory, at address 8000 or about 32K is where the process's memory is located in physical memory. In order to get the physical address, we need to add the virtual address to this base register, which gives us a physical address of 8,400. At this point, the CPU now has the actual physical memory address where the data is located. Now, all of this, these two comparisons, this comparison and this addition here, happens as part of the memory access instruction. So the process is running this instruction. It knows that it's trying to access this virtual address 400, but it doesn't see, this instruction doesn't see the actual address translation that happens here, or the access to this that puts it into register A0 here. All the process knows is the data from this virtual address got put into the register. So we've got transparency. We also have control because we test to see if this is within bounds. And finally, it is efficient because really all we're doing is two operations, a comparison and an addition, which if you remember back in your 2810 days, both these operations within hardware are actually very quick. This can be done with just a few gates, and this can be done with an adder. Okay, so let's actually, no, we went back here. So let's go ahead and figure out what will happen if we try to do something out of bounds. How do we keep this within the address space? So the first thing to realize is we don't have any concept of negative memory addresses. All the memory addresses are positive, unsigned integers. And so how do we go back up in memory? Well, we can't. There's just no way to give us a negative virtual address that would subtract instead of add. But because every address is checked against this bound register, we can actually make sure it doesn't go past the end by just simply doing something whenever this comparison fails. So let's take this example here. I've changed this instruction. Instead of starting at 100, it's starting at 5,000. And it's trying to load memory from 5,000 or past the address space. Well, here we have the memory address being compared. So when we perform this check, to make sure that the bound is greater than virtual address and find that it is not greater than virtual address, that the virtual address is actually greater than bound, we fail this condition. So what do we do when it fails? Well, what happens is the kernel, or the CPU, the operating system CPU, does not allow that instruction to continue running. What it does is it actually calls what is called a memory fault handler. So the operating system kernel has a special routine that takes care of these memory faults. And the CPU, instead of running that instruction or accessing that memory, just simply calls this operating system kernel fault handler. And it does that in a very simple manner. It changes the program counter. So instead of running whatever instruction comes after this load, which is probably at address 100 or virtual address 108, it sets the program counter to the kernel fault handler. Now, where does it find this particular value? Where does it find the address for this fault handler? That is set by the operating system kernel, and we'll talk more about that shortly. So, using these base and bound registers, we can now relocate processes to an entirely different physical address. So we see here that a process, in this particular process, has an address space from 0 to 16K. It is located in 32 at location of physical memory of 32 kilobytes. Consider for a moment what would happen if we copied this 16K of memory up here to this 16K, freeing up this, or putting all of the process memory in this particular block, starting from 16K and going to 32K in physical memory. If we copied all of this and then just changed the base register to 16K, the process will still see its address space starting at 0 and ending at 16K, and the hardware will make sure the proper addresses are translated. We now have the ability to dynamically relocate processes in physical memory. This is very useful for lots of reasons. Let's say, for example, this process here, which is 16K, is blocking us from using either of those pieces of memory for a 32K process. If we wanted to load a 32K process, how do we do it? Well, if we move this process's memory up here to 16K, it frees up this block and allows these two blocks to be allocated in a line. Now, there's a term for this. We'll talk more about this. When you have two blocks in physical memory like this, we call this external fragmentation. This is fragmentation that is outside of a memory's address space. So external fragmentation usually happens when one memory block divides up physical memory so that it can't be used. There's another case where we have memory inside the process that is not in use. It has been allocated for the process, it's part of the address space, but the process isn't using it. And this could be very large. We call this internal fragmentation. And again, we'll talk more about these fragmentations later. But the point of this conversation is that we can now move processes around just because we have two registers that tell us where the virtual memory address space is. So, how do we prevent a process from screwing around with these two registers? A process should not be able to modify the base and bound. If it could set a higher bound and access memory after the address. So if it set a higher bound over here, it can start accessing memory after its address space. Or if this process could run the instruction to change the base register, it could actually start accessing memory before it, or even the operating system in this case. So what we need to do is prevent the process from modifying those two registers. We do this by using what is called privileged instructions. Privileged instructions can only be executed whenever the actual CPU is set to a special mode. There are two modes. There's kernel mode. Kernel mode has access to those privileged instructions. And then user mode does not have access. When the process is running, the CPU is in user mode. And if it tries to access one of those privileged instructions, then the operating system's fault handler is called. We talked about the fault handler for memory. Now we have a second fault handler for illegal instructions. When a system call is made or an interrupt happens, that returns control to the operating system, and the operating system will be switched into kernel mode. When the operating system is in kernel mode, it can access these privileged instructions, which allows it to modify the base and bound register. This is necessary because the operating system may need to switch the process context. So maybe it needs to switch from this process, which is at 32 kilobytes, to another process that is in memory. Say there's one here in 16 kilobytes. The operating system would use these privileged instructions to change the base register to 16 kilobytes and then return control back to the process, switching to the user mode so that when this process runs, it will run in the user mode. So, what hardware do we need to make this work? We need some sort of privileged mode. So, this privileged mode is going to allow the operating system kernel and prevent the user process from executing privileged instructions. Privileged mode will also throw an exception whenever we access it. So, hardware must have a way to switch between a privileged mode and a non-privileged mode. To have virtual memory, we need base and bound registers of some sort. This is needed for the CPU to support address translation and bound checking. So, if we have the base and bound registers, now we need hardware that does the address translation and bound checking, which is special circuitry in the CPU that will A, validate every virtual memory address, and then perform the addition to do the address translation. Again, very quick operations, very simple circuitry to perform this within the CPU. We also need hardware to to actually change the base and bound registers. This is the instruction that the operating system will use to modify these every time a process is changed, or every time a scheduling operation happens. We also need hardware for specifying the operating system fault handler. Remember that function address? That function address for the fault handler needs to be stored somewhere, but we do not want the user space process to be able to store that. So there must be a privileged instruction for saving the fault handler address in a register that will allow the fault handler to be called, or somewhere in memory. And this usually happens before any processes are run. So the operating system on boot will set the fault handler function, and then it will schedule the first user space process. And then, of course, we need some hardware that will be able to change the next instruction address or the program counter when a fault happens. This is not going to be any privileged instruction at all. This is just simply going to be the CPU setting a new program counter to the operating system where the operating system stored this address. So with these 6 pieces of hardware, we can support virtual memory. And what does the operating system need now that the hardware supports it? Well, the operating system needs to assign virtual memory to a new process. Okay, so it needs to be able to figure out where there's memory in physical memory to assign to processes. This is usually done through what is called a free list, and we'll talk more about different kinds of free lists when we get into more complicated memories. But an operating system keeps track of a free list, and when a new process is created, it allocates a block to that process and modifies the free list. The operating system needs to change the base and bound registers at each context switch. So whenever a process is being scheduled and it's already been allocated memory, the operating system will change the base and bound register for the specific process and then allow the process to execute. Finally, the operating system needs to handle faults, and we had two different faults that we talked about, both the address or the virtual memory access fault as well as the illegal instruction fault. The operating system first needs to initialize the hardware with these addresses, and then the operating system should have functions to handle both memory access faults and illegal instruction faults. Now, what does the operating system usually do in these particular cases? The operating system will normally kill that program, terminate it. Basically, it will clean up the memory for that process and never run it again. Also, that particular process will very likely have the operating system will report an error message indicating that the process has been terminated. We call those announcements panics. So let's talk a little bit about what the kernel needs to do when it's starting up. This is before we ever run one process. It starts by first initializing what is called the trap table. This trap table will handle our illegal memory accesses and our illegal instruction accesses. But there are other things the trap does. Remember, the CPU has this timer, and when the timer goes off, a function in the operating system needs to be called. How does it find that function? Well, that's initialized in the trap table at a specific location. Thus, when the timer goes off, there's an address in the operating system that will handle whatever the timer is supposed to do. Finally, there is also a system call handler. When a user space program wants some functionality from the current operating system kernel, rather than trying to call a function directly in the operating system, it will do what is called a system call. Well, system calls are handled through the trap table. So when I perform a system call, the actual CPU switches to whatever the address, the function address for the system call handler is, and then allows the operating system to take care of that system call. Once the trap table is initialized, then the operating system can start the timer. The timer for XV6 is initialized for every 1/10 of a second. And actually, this timer is set different for every operating system and every type of scheduler. So for our operating system, every 1/10 of a second. Other operating systems don't set a timer this frequently or do it differently. Finally, once the timer is set, it initializes the process table, basically taking care in like in XV6, writing all the empty information and the unused flags in the state for all the processes. And then it initializes the free memory list. All of this happens before one process is run. Before any user process runs, this is what the operating system needs to do. This brings us to the end of Chapter 15, where we talk about address translation.